why we need quantum field theory. Okay, so you are not here. Okay, so let's build up the notation. So we describe an event. Let's say, so event means, so you label it by certain coordinates like this in C, T, X, Y, Z. Okay. So then I can define an interval between two events. Let's say I'm having an event CT X, Y, Z. So and CT plus dt. Okay. And X plus dx, Y plus dy, Z plus dz. Okay. So these are two events infinitesimally close to each other. Okay. Then we can define an interval ds squared like this thing. Okay, so this is an invariant quantity. Okay, so we define it like this thing. So there are two ways to define it. Okay, so this is one way, but we will. Okay, so we will be using this kind of interval, or we define it this way as well: minus c square dt square plus dx square plus dy square. Both are correct. There is no problem. Okay, so most field theory people use this kind of convention. Okay, and this is convention followed by general relativity people. Okay, so both are the things. We'll be using this kind of object. Okay, so this defines our interval. Now let me define. Okay, so about this very interval, this interval signifies the constancy of the speed of light. Okay, clear? And we'll be having these kinds of intervals, ds square. Let's say if it is equal to 0, so that means the signal is going at the velocity of light, or the particle is moving at the velocity of light. Okay, so we call them as light-like or null. Okay, trajectories. If a particle is following a trajectory for which this ds square is equal to 0, then we call them as the light-like trajectory or the null trajectories. Clear? Okay, or we call the events to be light-like or null events. If you are having this ds square, let's say greater than 0, so we call it as a time-like. Okay, so this is a time-like event. It means the particle moves at a velocity less than velocity of light. So here you can always find the velocity of a particle less than velocity of light. Clear? And then you are having another kind of interval, ds square less than 0. If I define it this way, okay, so if I define it this way, then it will change. Okay, then this will remain the same thing. This will become space-like, and this will become, okay, so we call this as a space-like. The definition changes with the definition of the interval. Okay, be careful, huh? Okay, so we call this as a space-like event. Here we always find the velocity greater than velocity of light. Clear? So this is what you know already. Okay. So let me define a quantity, what we call it as a 4 vector. Okay. So we will usually call it as a Lorentz 4 vector. Okay. So that means it transforms in a certain way under Lorentz transformations. So let me define a notation. So x mu is some 4 vector. Clear? So let's call its coordinates to be some x0, x, okay, x1, x2, and x3. So it is having 4 components. One is the time component, temporal component. Another 3 are the space component. This is how we define a 4 vector. Okay. So here I will define this x mu. So you can think it as a coordinate. Okay. So you label it by the time, and then x, y, and z. So I will write it as c. Okay, so as a vector x. So when I use the vector notation on something, that means it's a 3 vector. Okay, when I don't use a vector notation, it means a 4 vector. Let's say if I write x and this x. So the difference between the two as we go along the course, so this will be treated as a 4 vector and this will be treated as a 3 vector. Clear? So for 3 vectors, I will explicitly use arrows. Got it? So now, if I okay, so yes, if you have done this kind of business for vectors, so let me revise what exactly these things mean. So you always write a given vector with respect to a basis. Although vector is an abstract concept, okay, it's some geometrical object, it's a vector. But if you try to get its meaning, you need to figure out a basis. Okay, in a given basis, you need to figure out exactly what it means, what these x0, x1, x2, and x3 means. Okay, so let me start with an example, then you may be able to understand it. So you have heard about this direct lattice and the reciprocal lattice. Okay, so let's say if you are having a lattice vector described by, let's say, E1, or let me write E1, these are the unit vectors E2 and E3. So these are the unit vectors specifying the directions along x, y, and z axis. Clear? Now from this I can construct what we call as a dual basis. Okay, another basis. Think of, okay, so think of a curved surface. Okay, at a given point we can construct the direction of that point using either a tangent or a normal to that surface. Clear? Got it? Similarly is here. So if you are having a direct basis, you can construct what we call as a dual basis. Okay, so you construct a dual basis. So let's call that dual basis E1, E2, and E3. So what is that? So this is just labeling. So don't so upper and lower indices, they are just labeling. Okay, if you are afraid of that, so forget these things. You can write it as a capital E, capital E1, capital E2, and capital E3, so on. Clear? So what is this equal to? If you remember, it's something E1, okay, E2 cross E3, is it? Divided by the magnitude of this thing. Okay, E2 cross E3, something like this, and so on. Got it? So that means if I am giving you a vector, you can construct its projections along two types of bases. Samashivan, you can define a vector in terms of this basis. Let's say I am having a vector. Okay, got it? So I can expand this vector. If this is a basis, then I can expand a vector in terms of the basis. So let me write that as a V1, E1 plus V2, E2 in this basis. So, or you can say I can construct, okay, I can, expand this vector in terms of this basis. Let me write it this way. Got it? So, either you expand your vector in terms, think of a tangent space, or that in terms of the tangents or in terms of the normals. Got it? Okay. So, like this way. So, now you identify actually two different types of components for a given vector. Okay, that means two types of descriptions are available. Okay, so one set of components, this V1, V2, V3, we call as a contravariant components of the vector. That means these are the components defined in the direct basis or defined in the tangent basis. Clear? And so these we call as a covariant components. They are defined in the dual basis. So this is the simplest of way to understand this kind of notation. So I am defining now a 4 vector, okay, a contravariant 4 vector, okay, like this. So this should you should now understand what the definition means. Okay, a contravariant vector and a covariant vector. Okay, so this is from the perspective if you expand a vector in terms of basis. Another perspective is due to rotations. Okay, how you define a vector based on the rotations? So let's say if you make a coordinate transformation, if the basis vector change under certain way, now you take any arbitrary quantity, let's say it has some components. Let's think of a 2-component object. Okay, you are having a 2-dimensional x and y, you rotate your coordinate system. You know the transformation between the old and the new coordinates, is it? X prime is equal to x cosine theta plus y sine theta and so on, is it? Now you take another quantity. Let's say you take a v, it is having 2 components. If those components transform in the same way as this x, y are transforming, then you call it as a vector. So this is how we define a vector based on the transformations. Now based on the transformations, we can define these contravariant and the covariant components. Clear? So what it means, let's say your basis, a given basis transforms in certain way. Okay, now if the components of the vector transforms in the same way as the basis is changing or the basis is transforming, clear? Then we call it as a covariant components of the vector. Now if they are changing in an opposite way, in the contravariant way, in a contrary fashion, clear? Then we call it as a contravariant components of the vector. So this is a fundamental definition, clear? Okay. So any confusion? So let's go ahead. Okay. So let me introduce now what we call as a Lorentz 4 vector. Okay. So forget about Lorentz 4 vector. I mean Lorentz term. Call it as a 4 vector. It's having 4 components this way. Okay, and I will call it as a contravariant vector. Okay, this is how I will define it. Now, okay, so if I have defined a contravariant vector, from this contravariant I should be able to go to a covariant. So if this is a contravariant, okay, so I need to go to the covariant vector. Okay, so there exists a relation between the two. How we define that relation? It is defined in terms of a metric. Okay, we introduce some another quantity. Okay, and so let's write. So let me write that as eta. Since we are in the flat space time, okay, I will tell you in a moment what that means. So let me write some quantity, some eta as a matrix. Okay, which acts on this thing, this x mu. Okay, so it gives me this x mu. Let's say x mu. Okay, so you need to adjust the indices on this thing. Let's write it as eta nu. Okay, and there is a sum over actually this mu. Everybody? Okay, so a relation exists between a contravariant and a covariant components by introducing what? A quantity which we call as a metric tensor. Okay, so which is defined this way. Okay. Samajh? Okay, so we will use the notation whenever there is a repeated index. Okay, so this is an index, it is down, and this is an up index. So this there is okay. So there is a sum over this repeated index. We will not use this explicit summation. Okay, notation. We'll simply use what we call as the Einstein summation convention. That means I will be writing this x mu as eta mu nu and x mu. So this is how we define the covariant part. Clear? So I need to figure out, okay, for a given space time or for a given background, this eta has a value. How to construct the value? Okay. So let's write. So I am having this ds square. Okay, so I write it as c square dt square minus dx square minus dy square minus dz. Clear? Okay, so this is actually defined this way. Eta mu nu dx mu and dx. This is just a simple, review as you have done it already. I assume you have done it. Yes. Okay, good. So there is a sum over this mu and nu. Okay, so actually this ds square is defined in this fashion. Okay, and I need so this very interval is defined for the flat space time. Okay, got it? Flat space time in a sense, because there is no dependency. There is no function multiplying this dt square, no function multiplying this dx square. All the coefficients which arise with this dt square, dx square, dy square, dz square are constants. Clear? So if they depend on in a non-trivial way on this tx, y, z, okay, then you cannot say it's a flat space time. You need to look carefully what exactly it is. Okay, got it? Okay, so now let's expand this very objective by our definition. Okay, so let's expand it. So it will be eta. So there is a sum. So how many terms will be there? So mu and nu go from 0 to 3. Is it? So we have defined it this way. This x mu as what? x0, x1, x2 and x3. So mu goes from 0 to 3. How many terms are there? 16 terms. Clear? So let's write it. So one term will be d eta 0 0 dx 0 dx 0. So let me write diagonal terms first. dx1 dx1 plus eta 2 2 dx2 dx2 plus eta 3 3 dx3 dx3 plus, so then there will be term eta 0 1 dx 0 dx1 plus all other terms. So you are having all other terms. Clear? So I require only these things. Now what this object is? dx 0 dx 0. So it is c dt, it is c square dt square. So this very object is what? C square dt square. This object is what? Dx square. This object is dy square, and this object is dz square. So now you can compare with this thing. So what you will get? Eta 0 0 is 1. Okay. So my eta 0 0 is plus 1. Then you are having eta 1 1 as minus 1. Then eta 2 2 as minus 1. Eta 3 3 as minus 1. All other etas are 0. Okay? Samajh aa? Okay. So let's try it. So I will write then. So what is the form of this eta? It's now a 2 by 2 matrix. So we'll not use the word tensors explicitly here. So later on, wherever it is required, so we'll call this simply as a matrix for the time being. It is 1 0 0 0 0 minus 1 0 0 0 0 minus 1 0 minus 1 0 0. Okay? Got it? So now you can construct that x mu. So let's construct this x mu. So, okay, so using this thing. So let's construct. Okay, so let's construct it. So how many equations are there? There are 4 equations, is it? So let's take mu equal to 0. So it is x0. So it will be eta. Since mu is 0, so nu x. Clear? Samajh aa? So there is a sum over nu. This nu is a free index, because it appears there is no sum. It is not repeated anywhere. Okay? So it is on the left hand side as well as on the right hand side. Okay, so this nu is a repeated index. By the way, you should always remember a repeated index. So appear. Okay, so if you see an expression where there is there is a sum over a repeated index. Okay, where it is you are having a contravariant and covariant kind of components, then the indices always appear one as lower and another as upper. Okay, so you should always remember this thing. Okay, so in the this tensorial notation. But if it is mentioned, let's say if there is no tensorial notation, let's say you are having eta ij xj, let's say for example, and there is a repeated length j, and if I am saying there is a sum over j, then it's implied. Clear? So it's not a tensorial notation. In a tensorial notation, it should be always a covariant and a contravariant. Okay, we call this as a contraction. Okay, in a tensor formalism, we call this as a contraction, the index which is being summed. Okay, so now you write this objective. So it is 0 0 x0 plus eta 0 1 x1 plus eta 0 2 x2 plus eta 0 3 x3. So what is this objective? So this is 0. So this is 0. This is 0. Okay, so this is equal to 1. So it is x0 is what? X0. So that means, okay, so I have got the 0 component does not change. So it is same as what you define for the contravariant. So let me write mu is equal to I. So that's 1 2 3. Okay? So okay. So I will write it as xi as eta I nu. I is fixed. Okay? So what I will write it as x nu. So I can write it as eta I0 x0 plus eta I1 x1 plus eta okay I2. So let me write this way in a detailed fashion. Okay, x3. So if I take I is equal to 1, so eta 1 0 is 0. So eta 1 1 is minus 1. So and eta 1 2 is 0. Eta 1 3 is 0. So in that case, so what we got? So I am getting, okay. So let me write. So x0 we have got as x0. Now if I write x1, so it is eta 1 1 x1, so it's minus x1. Clear? Now if I write x2, so what that is minus x2. If I write x3, that is minus x3. Samajh aa? Okay. So what therefore is, so if you are having now a contravariant like this thing, contravariant components of the vector as ct, x, y and z. Okay, so how you get now the covariant? So it will remain as ct, this will become minus x, minus y and minus z. Clear? So okay, so now let me define a dot product. Okay, so let's say if you are having now a 4 vector, okay, a 4 vector, let's say a mu as a0 and vector a, and another 4 vector as b mu as b0 and vector b. Clear? Samajh aa? So the dot product between the two, it is like this thing, a scalar product of what we call a mu and b mu. So this I define as this way, a dot b without the vectors on, without the vector notation. Clear? So this a dot b means what? Scalar product between 4 vectors. Clear? Okay. So how I write this thing? So you write this object as, so how you write it as? So you put as a0 b0 plus a1 b1. So let's write in detailed fashion, a2 b2 plus a3 b3. Clear? Everybody? So this I can write simply a0 b0. Let's write. So a1 I will write as such. Okay, so let's figure out what is b1. So because this b1, okay, so the special components are vector b. Okay, so when you put this down, so it will become as a minus. So it will be minus b1, so plus a2 minus b2 plus a3 minus. Clear? So it is actually equal to a naught b naught minus vector a dot b. Clear? So remember this thing. Okay. So now let's write the norm of the vector, the length of the vector itself. So you can write now the length. So I'll write now the a dot a. So how I write that is a mu. Clear? Got it? So how I write it? So just replace it. So it is a0 a0. Clear? Minus a dot a dot. Okay. So what is a0 a0? It is simply a0 square. Whether you write 0 upper or lower. Okay. There is no problem. Okay. So minus magnitude of a square. So this is how we write the norm of the. Clear? So now if this dot product, this a mu, if you see, this actually is the length of the vector. If this is positive, if this is negative, or if it is 0, you define it as time like, space like, or null. Clear? Got it? Okay. Okay, so there are other things you need to know. Yes. So now let's write this thing. So let's figure out what is the inverse of this eta. Okay. So we are having this very object. What is this x mu now? It is the length of the vector. Clear? Square of the length of the vector. So norm of the vector is always an invariant quantity if you make a transformation. Clear? So I need to introduce first transformation, then we'll go ahead. Okay. So first let's introduce a transformation. Okay, so let's go to the Lorentz transformation first. So then let's go to the Lorentz transformation. Okay. So whatever what you know the Lorentz transformation, those we call as a boost rule. So let's say if you are having two frames of reference, one frame is moving with respect to the first frame. Let's say A and B frames. So if B is moving with respect to A frame, let's assume along X direction with certain velocity, that means the B frame has been boosted by certain velocity. We call that as a boost transformation. Okay, Lorentz transformations, okay, means rotations as well as the boosts. So you can rotate your coordinate system in 4-dimensional space time. Okay, you can have a boost, arbitrary boost along any direction. Clear? So the set of the two things, boosts plus rotations, gives you the Lorentz transformation. Okay, so let's go to the boosts first. So what you know, so boost along X direction. So I will go in detail on the Lorentz transformation, so you don't need to worry. So for the time being, we'll consider as a notation. Okay, so how I write? So you are having this T prime goes as gamma times, okay, T minus V by C X square. Is it? Is it X square or X? X. Sorry. V by C square. Okay, and what is our gamma? 1 divided by root of 1 minus V square by C square. Okay, so then you are having X prime as gamma times X minus Vt. You are having Y prime as Y and Z prime as Z, because you are considering only the motion along X direction. Okay. So let's rewrite it in terms of our notation. So I can write it as this way. So let me write it here. So I can introduce C here. You introduce C here. So like this. Clear? So one C I have taken. So you introduce here C and C here. Okay. So now you can define. Okay. So this very transformation I can write like this thing. So what is Ct prime? It is x naught. Ct is our x naught. So I can write it as x naught prime. So this is our x1 prime. Then you are having x2 prime, and you are having x3 prime. So let's write it in the matrix form. So what is okay, so what it is multiplying? Ct. Ct is our x naught. Then you are having x1, you are having x2, and you are having x3. So what is multiplying Ct? It's gamma. So it will be simply gamma. Then you are having minus V by C. So let me write that as a minus beta gamma. So this will be minus beta gamma, gamma 0, 0, 0, 0. So you are having 0, 0, 1, 0, 0, 0, 0, 1. What is our beta? V by C. Clear? So now if you see, there is actually a matrix structure. So the boost, this is we call as a boost matrix. Clear? So this is a boost along X direction. Okay, so now you are having a components of a 4 vector. When you boost to your coordinate system, the components of your 4 vector transform in this way. Okay, so in other words, if I am having, let's say, okay, so let's say if I am having now a 4 vector, okay, x mu is a 4 vector. So let's make an arbitrary transformation. Let's make an arbitrary Lorentz transformation. Clear? That will be actually a 4 by 4 matrix acting on the 4 vector. So this is actually a 4 by 4 matrix. Okay. So this is our 4 cross 1, and this is our 4 cross 1. Okay. So the column vector. So now you see this is actually our column vector. We can treat it as. So it goes as. So when you make a transformation, let's say to a primate coordinate system. So it goes as x prime mu. So let's introduce a transformation matrix as lambda, okay, and then let me introduce the same thing, okay, x. Clear? So for this I will use an index nu, okay, it's a column vector. Now what are the indices I will be using here? Because I'm okay. So here is important point, because I am going from a contravariant 4 vector to a contravariant 4 vector. So you are moving from the contravariant components to the contravariant. They do not mix up by any linear transformations. By any kind of transformations, contravariant does not mix up with what? Covariant ones. Contravariant will always remain as a contravariant, and covariant will remain always as covariant. Really? So you go from, let's say these are the contravariant components, you move to the contravariant components through this kind of matrix. Really? So what is the, okay, so that is a matrix multiplication. Okay, so you need to introduce now the indices of a matrix. Clear? Think it as a matrix. Clear? Okay. So, but if you see, this is actually the muth element of a matrix on the left hand side. So, when you compute this very matrix product, you should get actually muth component. Okay? And why mu exists? It is the above one. Huh? Okay, so you put this mu here because there is only one place where you can put it. So, समझ आओ? Okay, so why you are having nu here because it's a matrix product with lambda and x, so you need to put nu here. So you can think this simply as a mu as a column, column components, okay, and nu as the row components. So समझ आओ? Got it? Okay. So this is simply our matrix multiplication. That's why nu is here contracted. Okay. So this is a general. Okay, so we call this as a general Lorentz transform matrix. Okay, so let's figure out what this lambda mu nu is for this kind of transformation. Okay, so everybody followed it? Yes. Okay. So any 4 vector will transform under Lorentz transform this way. Remember this kind of equation. Okay. So let's compute it for this very object. So let me take x prime 0. So what is that equal to? So let's compute. Okay, so let's compute lambda mu nu for boost along x direction. Okay. So let's put it. Okay. So it's x prime 0 is equal to, let's take the 0th component. Okay. So that's lambda 0 nu x nu. Okay. So how I can write it as lambda 0. So there is a sum. So you write, okay, most of the books put it this index down to this mu. Huh? So, but if you look at the older books, they will put this mu a little bit deviated. Huh? So just to differentiate between, you can think it as a column vector and this as a row vector. Okay, row index and the column index. Okay, you can identify mu and nu with the rows and columns of a given matrix. Okay, but if you put more number of indices, then it will become problem. Okay, so okay, so let's keep it as a, let's put them as up down. Okay, so it is 0 0 x 0 plus lambda 0 1 x 1 plus lambda 0 2 x 2 plus lambda 0 3 x 3. Okay, so now let's compare it with this thing. What is our x 0? Gamma times x 0. So from here, so I'm having x prime 0 as gamma x 0 minus beta gamma x1. Rest are 0. Okay, so what is our lambda 0 0 then? So which implies lambda 0 0 is equal to gamma. Okay, because gamma is multiplying x naught. And what is our lambda 0 1? That's equal to minus beta gamma. And what about others? Lambda 0 2 is equal to 0. Lambda 0 3 is equal to 0. So similarly, we can see the others. So let's write now this x prime 1. Okay, so what is x prime 1? It will be lambda 1 nu x nu. Okay, so you can now identify. So let's identify lambda 1 0. So lambda 1 0 is this very object. Okay, so it will be minus beta gamma. So which implies lambda 1 0 equal to minus beta gamma. Then you are having lambda 1 1, it is equal to gamma. And what is lambda 1 2? That is 0. Lambda 1 3, that's equal to 0. So similarly, you can see lambda 2 2, that's equal to 1. Lambda 3 3, that's equal to 1. All others are what? 0. Okay, so this is how we identify this lambda for a given boost. Okay. Okay, so let's move to this very transformation again. Okay, so have you written it? So okay, so let's move to that very lambda. So I am having this kind of matrix. Okay, so let me write gamma minus beta gamma 0 0 minus beta gamma 0 0. Okay, so I will consider only 2 by 2 part. So because others are 1, so they are not required for me. So let me take only this very part because I need to tell you something. Okay, rest, because the rest will not be changed with our analysis. Rest will be there. Okay, so what this is equal to? So I can write this as um, gamma. Okay, 1 0 0 1. Can I write it? Minus beta gamma. Can I write it like this way? So let me put it this way. Plus beta gamma 0 minus 1 minus 1 0. Okay. So what is our beta? V by C. Okay. What is our gamma? 1 by root of 1 minus V by C square. So this is actually a finite boost. Finite boost means you are boosting your particle by a finite velocity. Okay. So that means it has traveled a finite distance from origin to that point. Clear? So now let me consider the infinitesimal transformation. That means a small kind of transformation. Okay. So when I consider the infinitesimal transformation, so that means this beta, this V by C is very small. Okay. So if I consider now the infinitesimal transformation, so this is our finite one. So this is our finite transformation. Okay. So if I take infinitesimal 1 or the infinitesimal transformation, so that means my velocity is very small, beta is very small. So it means V by C is very less than 1. Okay. So what about this gamma? So which implies this gamma tends to 1 for the infinitesimal ones. Now let's look at this very matrix. So I am constructing the infinitesimal out of this very matrix. Okay. So that means if I give you a 2 by 2 matrix and I want you to identify the infinitesimal out of that matrix. Clear? So how it will look like? Okay. So let's look at this thing. So gamma minus beta gamma minus beta gamma gamma. So this will go as, so gamma will become 1, so it will be simply an identity matrix. So because this is an identity, plus beta, so let's write it as a beta. Okay, 0 minus 1 minus 1 and 0. Clear? So that means, so this is a small parameter, this beta. So this is a parameter what we change actually, because we are changing, and we can now increase the velocity so that to make this transformation to be finite. Okay. So now if I have to look at the infinitesimal transformation, how it should look like? There should exist an identity. It should be actually proportional to identity plus the first order correction of the parameter. Here the parameter is beta. So, samajh aawa? Okay, clear? Okay, so then we will look at, okay, since this is actually the correction to the lambda. Okay, so we will see in a moment. We will see, so this forms actually very important object for us, for our transformation. Okay, with the help of this very object, we will be able to construct the finite transformation. Clear? So if you know now the infinitesimal form of the matrix, we can construct what? The finite one. Okay, so let me give a prescription how to do the finite one. You put infinitesimal, then infinitesimal, then infinitesimal, then infinitesimal. Okay, large number of times. So you add up all these things, what you will get? Finite one. So that means what you need to do. You put this infinitesimal, then infinitesimal, that means the multiplication n times. And you need to look at the appropriate power limit, so you will figure out that kind of transformation. Okay, so let's go to the general one. Okay. Okay, so let me go to the okay, these transformations again. So our transformation, Lorentz transformations are like this. Okay, so this is a general Lorentz transformation matrix. Clear? So I will tell. Okay, so we'll see in detail. This is actually both rotations as well as what boosts. Okay, if you see, look at this thing. Look at this very matrix carefully. So if you want to understand, so partition this. Figure out the only special components. Clear? Okay. So what is there? So it is actually the 3/3 rotation. Clear? Okay. So if you see, these gives you all, because these are the components which depend on this parameter beta. Here the beta is the parameter only. Beta is a velocity, because gamma itself depends on beta. Gamma is root of 1 minus beta square. Clear? So that means they depend on beta. So these factors do not depend on beta. So they will give you the rotations and they will give you the boosts. Clear? But you can extend this to the 4-dimensional as well if you don't consider any kind of boost. Okay, so that means you are putting all these things to be equal to 0. It will be a 4/4 matrix. Only the only the special components will be non-zero. Got it? Okay. So let's look at the infinitesimal transformation here. Okay. So let's look at the infinitesimal Lorentz transformation. Okay. Okay. So how I write it? So you are having now lambda mu nu. I need to look at its what? Okay. So let me write this way. This is a matrix. Okay. So let's write lambda mu nu for the time being. Then we'll use this notation. Lambda is our matrix. I want to figure out what is its infinitesimal form. How it should look like. An identity matrix plus some correction. Clear? So what is our identity here? A constant matrix. So that's our eta. Okay? So in 4 dimensions, it's what? Eta mu nu. Samajh aaga? Then let me put some correction. Okay? So up to the first order, omega mu nu. And we will figure out for this kind of matrix what this omega mu nu is. We have seen actually that. That's that minus beta kind of thing. Okay, but we don't know. Okay, we only know this very object and we don't know the properties of this kind of object. Okay, so let's try to figure out what is the property of this very object. Any problem? Okay, so let's let's do this thing. So what to do? Okay, so have I missed something? Because I am not told you that. Have I missed something? Yes, because I don't know actually the properties of this eta as well. I have not constructed any kind of property of this thing. First, I need to specify the properties of this eta. I assumed, but I need to specify here. Okay. So before going back, okay. So first thing is this eta mu nu is symmetric. Okay. So it is a symmetric object. Symmetric under exchange of mu and mu. Can you identify it? It is symmetric because it's a diagonal matrix. Diagonal matrix is always symmetric. Okay. Okay. And so, but if you are having a non-diagonal as well, it is still what? Symmetric. Let me tell you how. So you write this ds square as eta mu nu dx mu and dx mu. Clear? Okay. So this product is actually a symmetric product. Because of this symmetric product, this must be what? Symmetric. Otherwise, it's if this is if this is antisymmetric and this is symmetric, then this product is equal to 0. Got it? So that means if this is symmetric, this must be what? Symmetric. So this is the simplest of the ways. Okay, so next, let's try to figure out its inverse. Okay? So before that, so I am having this kind of object x mu and x mu. So this is what? The length of the vector. Length of a vector. Okay? It is a scalar. So it's a scalar under Lorentz transformation. So when you apply the Lorentz transformation, that means this is actually a scalar. So let's figure out the conditions using this kind of scalar. Let's figure out the conditions on eta. Okay, that will help us to construct its inverse. Okay. So in primate frame of reference, so I will having like this x prime. Can I have? So because this is a scalar, this has to be same thing. What? This x mu, x mu. Clear? Okay. So how I can write it as? So I will write it as x prime mu because this is what? A covariant vector. So I will make it as a contravariant first. Okay? So I will write it as eta mu nu x prime. Sorry, x mu. Oh no, x prime nu. X prime, because I'm just changing the index. I'm not changing the frame. Huh? Okay, so this only means I'm changing the index, I'm not changing the frame of reference. Okay, so let's now change the frame of reference. So how I write this x prime mu? It says lambda mu, let's write it as alpha. Okay, then x alpha. Clear? Because I know the Lorentz transformation property of only the contravariant. So you can use the transformation property of the covariant. So you need to construct that. Clear? So for constructing that kind of object, so I still need this kind of transformation. Okay? So what I will do, I will simply use the transformation properties of the contravariant components. Okay? That's why I have changed the index. Okay? So I have made it contravariant. Okay, so now let's use the proper Lorentz transformation properties. This is x prime nu. So let's write it as a nu. Because this is a free index. So forget all this thing. This is a free index. You put this nu here. So let me write beta here and x beta. Clear? Okay. So what I will write it as eta mu nu. So then I am having lambda mu alpha, lambda nu beta. Okay? X alpha, x beta. Clear? So what this has to be equal to? This has to be equal to what? By definition, let's say x alpha, the same thing in the unprimed frame of reference. Whether you put as x mu or x alpha x, because it's a dummy index. Clear? So this I can write this very object as, so let's write it as eta alpha something, let's write sigma x alpha x. So let me write beta. Can I write it? Yes. Because it is a dummy index, I can put it. Okay, because they are the different terms. That's why I have put. So now you are having x alpha beta here, x alpha beta here. So what it means? So eta mu nu lambda mu alpha lambda nu beta is equal to eta alpha. So this is actually the property of this matrix gamma. Okay? So in other words, if you see, so what this eta is, it's actually a matrix. If I take, okay, now let's, okay, so let's apply this eta mu nu either on this thing or this thing. So this will bring mu here. So I will be having lambda nu alpha, clear? Then you will be having eta, okay, so lambda nu beta. Okay, so let me write it in a careful way. So this is very important identity. It says one lambda is actually the inverse of the other lambda. Okay, so if you are having the set of matrices, we satisfy, okay, let's take the set of matrices lambda. Okay, under multiplication, if they satisfy this kind of condition, they form a group that we'll be studying in the next lecture. Okay, so let's take it this way. So what is our eta mu nu doing? So it will bring mu down, because its work is what? Either to raise or lower the index. So it will bring this mu down, put nu here. So alpha, clear? Then you are having this lambda alpha, beta here, eta alpha beta. Sorry. So it should not be alpha mu. So it is
eta.
It's nu alpha. Sorry, it's what the index is here. It is nu. Yes, it's nu. Sorry. Okay. समझ रहा हूँ? Now what you can do? Okay, so let's raise this beta up, or you raise this alpha up. Okay. So let's raise this alpha up. So you can raise or lower. If you raise alpha from here, you raise it from here as well. So you put nu here, alpha here. I will make a distinction. Okay. So this is lambda nu beta. Clear? This is our original. So what that is? Eta alpha beta. Clear? So this eta alpha beta is what? It's actually identity matrix. So now let's check it. So you are having eta. Okay. What is our eta mu nu? So that's 1 minus 1 minus 1 minus 1. Clear? So let's raise 1 up. So when you take 0 component up, clear? Whether you raise 0 or lower 0, it does not change the sign. Clear? Okay, so that means I am having for 0, it's okay. It will remain. When you raise or lower what? The special index. So it will create a change in sign. Clear? So this minus 1 will become plus. So it will be like this thing. So this 1 will remain as such. This will become 1, 1, 1. What this is? identity. So this is simply our delta alpha beta. Clear? Now if you see, this is A multiplied by B is equal to identity. So it means this very object is inverse of this object. So in other words, lambda mu beta, its inverse is what?
Lambda alpha.
Okay, just tell me. Just interchange and this is lambda beta. Okay, so I am taking this. This is an equation. Okay, so what we identified this new? New we identified with the column, is it?
Yes.
Beta we identified with the rows. What we identified now? There is actually interchange of rows and columns. When you take the inverse, what is happening? Rows and columns get interchanged. So that's exactly what is happening. It's simply the transpose kind of thing. Okay?
Yes, inverse.
Got it? Samajh aaga? Okay. So this. Okay. So now let's go to the infinitesimal transformation. Everybody followed it?
Yes, sir.
Okay. So by the way, one more point. Since this is a diagonal matrix, it's okay. So if you have to go, let's say. So this I have not mentioned anywhere. Okay. So let me mention it here. We are running out of time. So you are having this eta mu nu. So you take from x nu to this x mu. Clear? So from contravariant to covariant. You can go to the covariant. Sorry, contravariant from covariant like this. Okay? And the condition between these two is eta nu lambda. So that is delta mu lambda. Okay? So that means this eta is inverse of this thing. Now let's take the inverse of the diagonal matrix. That is the same thing. So that means eta is same in both ways. Whether you take the upper indices or the lower indices. Now let's go to this. The infinitesimal transformations. So then we'll stop. So because that will be the last part of our notation. Now take this very thing. So what is our infinitesimal note? This transformation. Okay. So infinitesimal transformation is lambda nu mu. So what that is? Eta mu nu plus that omega mu mu. Now we have identified the properties of this lambda. It satisfies that equation. We have identified these properties of eta. Okay. Clear? And we need to identify the properties of this omega. Okay. So let's use in that very equation. Call this equation as 1. So is it clear what I am saying? Okay. So from equation 1 you are having eta mu nu. So what is this lambda mu alpha? So it will be eta mu alpha plus omega mu alpha. Clear? Then what you are having? Lambda nu beta. So it will be nu beta plus omega nu beta. So what that is equal to eta alpha beta. Okay? Samajh? So what it gives me? Eta mu nu. So let's multiply. So it is eta mu alpha, eta nu beta. Clear? Okay. Then you are having eta mu nu. Okay. Eta mu nu. Okay. Then this eta mu alpha, then omega nu beta. So I am going this way. Then you are having plus eta mu nu, omega mu alpha, eta nu beta. So then the other term is omega square. So that since it is an infinitesimal quantity, it's order of omega square. Clear? So that's equal to eta alpha beta. Okay, so now let's look at this very term carefully. So look here. So when you apply call this as a function, some function which is having upper index and lower index. So when you apply this eta mu nu, this mu is contracted. Okay, so it will lower down this mu and replace it by nu. So it will be simply eta nu alpha, then eta nu beta. Is it?
Yes, sir.
So now let's look again. So this eta nu will get contracted. So it will lower down this index. So what it gives me? Eta, it will remain eta alpha beta. Okay? And this very object, so that means this object cancels with this one. Okay, so now let's look at this thing. So this very thing. So eta mu nu. So mu is contracted. That means so it will bring down this mu here and replace it by nu. So it is eta nu alpha, omega nu beta. Okay. So now nu is contracted, is it? It will be lowered, so it gives me what? Omega alpha beta at a first place. Okay. So now let's look again this thing. So this object and this object. So what it gives me? So it is eta, nu is contracted, and mu beta. So omega mu alpha. So what you will get? Omega beta alpha. Really? Got it? So this is, everybody followed it? Okay, so what you have, just 2 minutes more, 2 to 5 minutes. What we are having, so which implies therefore omega alpha beta plus omega beta alpha is equal to 0. So what it gives me? Omega alpha beta is equal to minus, which implies omega alpha beta is antisymmetric under alpha beta exchange. Clear? So that means omega is what? Antisymmetric matrix. Got it? Okay. So now let's go to the matrix what we have. The example. So then it will help. So what was our example? Boost kind of. So this is very in general. So we'll take its properties later on. For the time being, you will understand this is what? An antisymmetric matrix. Clear? Okay, so the example what we have. So what was our this lambda? Okay, so we had that lambda. Okay, mu kind of thing. That was an identity matrix. Clear? So you are having this eta mu nu. Let me write plus. Then you had this beta, the parameter 0, -1, and 0. Clear? So this was the infinitesimal one. Okay. So what you are having actually? Omega alpha beta. But if you see, actually the indexes are up and low. So what is the index? So this matrix is actually omega mu nu. Is it? Utisha? Got it? Because indices are how? Mu is here, nu is here. But here, what are the indices? Either lower, you can put either both up. Samasha, you can put it this way as well, both up, like this thing, minus omega beta. There is no problem. Okay, because you are raising all the indices in the same way. Okay, so there is no problem. So now, so we have to bring it in this form. How to do? So tell me what is omega 0, 0? That is 0. What is omega 0, 1? That is minus beta. What is omega 1, 0? Minus beta. What is omega 1, 1? 0. Clear? So now, so I can write this, let's bring this 0 down. Omega 0, 0 will be 0. Because bringing down the temporal index does not change sign. So what you get? So you bring 0 down. Omega 0, 1, it is minus beta. Then omega, when you bring down 1, 0, what you will get? Plus sign. So it is plus beta. Okay? So what it is? Omega 1, 1, that's minus 0, that is simply 0. Clear? So what you are having now? This omega mu nu, that's simply equal to 0. Okay, minus beta, then plus beta, 0. Is this an antisymmetric? Is it antisymmetric? Huh? Omega 0, 0, omega 0, 1. Omega 1, 0 and omega 1, 1. Clear? So it is antisymmetric. Got it? So this is an example for it. Okay? So yes, little piece of notation. Little piece, then we'll stop. Huh? Okay. So we define another objective. So let's say momentum 4 vector. So this is the 4 momentum. Huh? 4 momentum. This we define this way. E by C and vector P, and you define the lower one as E by C and minus P. Okay. So if you take the scalar product, if you make the scalar out of this thing, so it will be simply E square by C square minus P square. Okay, so that is simply equal to M square C square. So you can see from the energy momentum relation. And another thing, you define this objective, partial mu, defined as partial by partial x mu. So it is the derivative, 4 derivative. It's not a covariant or contravariant derivative, it is simply a 4 derivative. Okay. So it is 1 by C, partial by partial t. Take the 0th element, 0 means like this thing. Then you take the special components, it is nebula. Here it is the opposite of this thing, huh? Because this is a lower index, so it comes with the positive this thing. So if I am having upper index like this thing, partial by partial x mu, okay? So remember, this is lower here, it means upper in the denominator. It is upper here, lower in the denominator. So it's 1 by c, partial by partial d minus lambda. So what it gives me, you can write now partial mu. So it is 1 by c square, partial 2 by partial t2 minus lambda square. So that's our DLN version. Okay, so this is all for today.